Hi, how are you doing? Okay, so I'm about to remake this video on excited versus ground state electron configurations because I made a really stupid mistake. And I think it was Carlisle Deaver who informed me, so thank you, Carlisle. I'm going to read this real quick, all right? So ground state configurations and electron configurations. No, excited. Ground state versus excited state configurations. I got this, I promise. Let me share my screen and come here. Zoom just 1 moment. Okay. So ground state versus excited state configurations. Every configuration you have written thus far is a ground state configuration. Okay. So what it means to be in the ground state, configuration, what it means to be in a ground state, you know, and in my head, it's not like the scientific definition, but it works. It's right. It's just not the scientific definition. Is the electrons are where you expect them to be. All right. They are at home. They're not really at home. Now, we never know exactly where an electron is. Heisenberg uncertainty principle. We never know exactly, but we can have an idea of where it probably is located, okay? So when we write our ground state electron configurations, we are writing exactly what we've always done. We're writing where you would expect to find the electrons. You're following the Aufbau sequence, right? The Aufbau sequence tells us the order in which they fill the electrons. We're looking for low energy states, right? Okay, now, so here's our nucleus. Let's draw some energy levels. Now, energy levels are not really orbits like this, okay? I say that. They're not. This is just a really good representation of how to visualize what's occurring. All right, electrons do not travel in perfect circles or orbits or anything like that. But this is just a really good way to see it in your head. For me, it is. I'll throw some little electrons out here, okay? They're just chilling out. They're just chilling out where we expect them to be, right? 2, 4, 6, 7, 8. We'll put a couple more out here. This will be magnesium, right? Well, he's just hanging out. The electrons are where you expect to find them. This is your nucleus in the center. It's positively charged. It's attracting those electrons, pull them in. Well, if we were to put, maybe shine some ultraviolet radiation on this atom with, you know, a really, really high frequency, a really short wavelength, it may just be enough energy to cause 1 or 2 of those electrons to move out to a higher energy level, right? And you see this electron, let's just move him right here, okay? We've already said, but that would be times HV. This would be times 3, you know, times HV, times HV, times HV, but that's not the moral today, okay? Today is excited versus ground state configurations. We are no longer in the ground state. Our electron is out here on an energy level higher than where he came from and an energy state higher than he came from. So he is now in an excited state. Previously, the electron was in his ground state, okay? The time. Sorry, guys. Previously, the electron was in its ground state and was where we expected it. It is no longer where we expect it, so the electron is in its excited state. So this electron is in the excited state, and this electron is also in the excited state, okay? They have gained energy, right? The electrons have gained energy, okay? Well, because they are in an excited state and are further away from the nucleus and have gained extra energy, hold on, let me write this. They're now more unstable, right? It's kind of like you doing a handstand. You put energy into getting your feet up, but you're not very stable. And eventually you're going to have to come back down to the ground. Well, we could think about that like this with these electrons. They have moved out to higher energy levels. They're not as stable, much more energetic. Eventually they're going to need to go home and like just chill out. So what they will do is they will leave that excited state and they will fall back down to their ground state. And they will leave this excited state and they will fall back down to the ground state. And in the process, the energy that was gained is lost, okay? The energy that was gained is lost. And remember, this whole unit started with us talking about light. Well, that energy is in the form of radiation, right? This energy here is in the form of radiation. That's light, okay? It's got wavelengths, it's got frequencies, it's got speeds, it's got energies, and it falls somewhere in that electromagnetic spectrum, right? And we know that there is a visible light part, and we know that our eyes can see it, and we see the colors blue. Oops, I did it the wrong way. Roy G. Biv. Red, right? We see red. If the wavelength corresponds to red, we see orange. If the wavelength corresponds to orange, we see yellow. If it's in fact a yellow wavelength, green, blue, and then we've got some indigo here, okay? So the color that this light that's given off from this electron moving from an excited state to the ground state has a wavelength and it has a frequency. And if that wavelength and frequency fall within this range, we can see it. It also falls within other ranges, and we've got devices that can pick that up, like spectra. And that's how they identify what elements are in, say, far away in the solar system. And they find stars and they want to know what elements are in those stars. Well, they can, well, there's a lot more to the story and I don't want to keep going. But if you're interested, I could tell you about it. Now, what I want to say is a ground state configuration for, let's say, magnesium, that we just said, would look like this: 1s2, 2s2, 2p6, 3s2. So let's assume, right, this is my ground state. Once again, ground state here. Oh, I already wrote that, my bad. And let's look at our valence electron. Let me undo that and get a different color. Let's look at our valence electron right here. And let's imagine that one of those electrons jumps out to what comes after 3s? 3p? Maybe we have 3p1 and 3s1. So we have 1s2, 2s2, 2p6, 3s1, 3p1. Okay, so we see that this is an excited state configuration. Now you will not have to determine what electrons will transition to what energy levels. That is not your job. It's beyond our realm. You just need to recognize that this is a possible excited state configuration. Okay. Do one more. 1s2. This is the one I messed up on, and I had to redo this video. 2p6, 3s2, 3p6, 4s2, 3d10. Well, let's see. Maybe two of these electrons want to move out to a higher energy level. Let's go ahead and abbreviate this neon, 3s2. Let's abbreviate this argon. Simplify it. You should be able to follow along. Argon, 4s2, 3d8. And in my last video, I wrote 4s2. Something more like a 4p2 might make better sense. Definitely not a 4s2. But anyhow, we see that they have 2 electrons have jumped out. It doesn't always have to be 2, maybe 1. Just recognize the excited versus the ground state, okay? Right on. And that's going to be it. And, you know, once again, this movement here and the colors that it creates are, they pertain to a particular element. Different elements give off different colors. So when you think of fireworks and you see the different colors of fireworks, it's this process here of the electrons. The different metals in the fireworks, different metals give off different colors due to their different electron arrangements and such. Okay. Okay, I'm going to go ahead and end it there. And you have a great evening.